Okay, so in the previous segment, we encountered the polar decomposition. This is a fundamental property of the deformations that underlie continuum mechanics. And as we will see as we move ahead, it is going to reappear at various points and give us further insight into the nature of not just of motion and deformation, but also the nature of constitutive material response, about what it means to write out the stresses and energies and so forth. For now, let me go back, take a step back towards our strain tensor, the Lagrange strain tensor, and say something about it. Okay. The Lagrange strain tensor E. Okay, remember that E is 1/2 C minus the isotropic tensor, but I want to write C as F transpose F right now. And we'll just remember that this is simply the right Cauchy-Green tensor C. The reason I've written it out as F transpose F here is that I want to demonstrate that this definition of strain is already fundamentally nonlinear in our deformation gradient, right? Because it involves an F transpose F, so you may think about it as being quadratic in the deformation gradient F. Okay, so first thing to note, this is quadratic in F. What this means is that this fundamental measure of our kinematics is already nonlinear. The kind of elasticity we are going to study as we get further into material response is what we will term nonlinear elasticity, which means we're not going to assume linear response. And we'll see in more detail what that means. But a very important aspect of the nonlinearity of elasticity is the fact that this strain tensor itself is already fundamentally nonlinear in our most primitive definition of deformation gradients and strain. Okay? So there's fundamental nonlinearity which is actually inescapable here. And we will see why it is inescapable. Actually, we'll see more about it right now. Okay, so we have this quadratic nature of E. What E does, because of its structure, is to fundamentally, in a mathematically exact manner, nullify the effect of rotations. Okay? What it does is to leave us with strains that reflect the effect only of stretching the material, not of rotating it. And you recall at the end of the last segment, we demonstrated that the deformation gradient F fundamentally involves rotations and stretches, always, right? Okay, so let's observe what E does. Okay, so recall the polar decomposition. Okay. I'm going to take a step that we already took in the previous segment. I'm essentially going to repeat it here, which is, okay, recall the polar decomposition, which is F equals Ru, right? Where R belongs to SO3 and U, we demonstrated is positive, sorry, we said U is symmetric. We also demonstrated that it's positive definite because its eigenvalues we've chosen to be positive, right? So we're going to indicate that with an S plus here, okay, implying that it's positive, definite, and symmetric. Okay, So what this implies for E is the following. Let's get back here. E, which is F transpose F, we know we can write F transpose as U transpose R transpose, as we saw in the previous segment. F remains RU minus isotropic tensor. And in a step that we employed in the last segment, we see that the effect of the rotations are nullified. The rotations essentially kill each other, right? Because of the fact that we have F transpose F in there in the definition of E. Furthermore, given the fact that U is symmetric, we have therefore that E is 1/2 U square minus the isotropic tensor. Okay? What this implies is, we've already said what it implies, but I'm going to state it, are the rotations imposed on material neighborhoods of X, right? So we have a neighborhood around a reference position X, and that neighborhood, as we saw at the end of the last segment, fundamentally does undergo rotation under the deformation, right? But that effect of the rotation has been mathematically exactly cancelled out in our definition of the strain here. So are the rotations imposed on material neighborhoods of X play no role in E. So what effect does this have? Let's suppose we have a rigid body motion. Okay, so now we're saying that the deformation or the motion of this material, of this block of our, the motion of this body, right? We have our basis here. Relative to this basis, our motion, the motion of our body can be described exactly as a rigid body motion, right? No distortion. Okay? So what this means is, now if you consider a rigid body motion. Okay, how is our rigid body motion defined? We saw quite a few segments ago that rigid body motion in general is defined as Ct, where C is a vector, plus a rotation tensor Q acting on X, right? Where Q belongs to SO3, it is a rotation, and C is a translation vector, right? But now, what is the F that arises from this motion? F, which is partial of phi with respect to reference position, is simply Q. Okay? We can also write this, by the way, as F equals Q times isotropic tensor, because the isotropic tensor comes for free. Q belongs to SO3, of course, and the isotropic tensor, we know, is symmetric, just like U, and the eigenvalues of the isotropic tensor are 1, 1, 1, and 1. Okay? And 1, 1, and 1 are positive real numbers. So the isotropic tensor here is serving the role of the stretch tensor U, of the right stretch tensor U. Okay? So just as we expect, just as we proved before, this deformation, a rigid motion, does admit the polar decomposition, does admit the right polar decomposition, okay? Because this belongs to S plus of 3, okay? It just so happens that the rotation is uniform across the entire body, right? The entire body is undergoing the same rotation. It's not like the one material point is undergoing one rotation and another one is undergoing another. Likewise, the entire body is undergoing a uniform stretch. The stretch is 1, right? Essentially, material vectors are not being stretched here, okay, in a rigid motion. Okay, what does this imply for E then? E, which is, in this case, 1/2 F transpose F, but F is just Q, so we have Q transpose Q minus isotropic tensor, which is dead zero, always, forever, right? So our body could be spinning around till the end of time. The strain, the Lagrange strain as measured in it, is going to be dead zero, always, okay? This matters because now, if we're looking ahead now a little, but then if we think of storing energy in this material because of its strains, well, the strains are 0. So if you think of a material that's unstrained as having no energy, that works, right? And that sort of ties in with our physical notion of what should happen in a rigid motion, right? There is no storage of elastic energy. Later on, we'll define these terms much more precisely, okay? So this is a good thing about our Lagrange strain tensor, right? It's 0 for a rigid motion. However, if you were to be doing infinitesimal strain, this would not be the case, okay? So if you were to be doing the infinitesimal strain theory, okay? In that case, epsilon is the strain tensor, the infinitesimal strain tensor, and we know from definition that epsilon is defined as 1/2 the gradient of u plus the gradient of u transpose. Okay? Let's see how this works out. Recall that phi can always be written as x plus u, where u is the displacement. Okay? Therefore, partial of phi with respect to x is the isotropic tensor plus the gradient of u with respect to the reference position. Okay? For our rigid motion, we're calling it a rigid body motion. Right? For rigid body motions, we have F equals Q, which is isotropic tensor plus partial of u with respect to x. The reason I've gone through this is to show us that the displacement gradient, which is what enters the definition of the infinitesimal strain, is q minus the isotropic tensor in this case. Okay? So epsilon is 1/2 q plus q transpose minus twice of the isotropic tensor. Okay? All right, just from the definition of epsilon involving the displacement gradient plus the displacement gradient transpose, and substituting there.